Hello and welcome back to Differential Equations after 2 weeks break, sponsored by the stupid spring break and the snow, following one after the other. So what do we have? We're venturing into the world of solving differential equations using power series, right? And the power series are the ones that are mainly used in the field because not all differential equations are nice. So majority of them today we have to solve using numerical methods, and then power series tend to be this very powerful way of solving. So most of your engineering work later on depends on you solving differential equations or using equations that are solved by power series or Laplace, which is our next chapter, chapter 4. Now let's take a look at definition of power series and how to solve differential equations by this. This is some of the really awesome stuff. We first understand what the power series is. That's all same stuff like in Calc 2. You have first the sequence, which is ordered list of numbers. So that's the sequence. And then you have series, which is sum of the sequence. Ordering is done through the number n, which is the counting number, so 1, 2, 3, 4. You can start at 0. So if I say that an is equal to exactly, so let's say n squared plus 1, then we can write the sequence of numbers, and the sequence of numbers will be if let's say n starts at 0, so it's 1, and then 2, and then 5, 10, that's 3, so 4, 16, 17, 26, and so on. So this would be the sequence of these numbers, and then the associated series of n squared plus 1 could be either finite or infinite. Now we are mainly interested in infinite series. Finite series are not interesting because they always converge, and you just add the amount of numbers that you have in that sequence. So this thing over here would be equal to 1 plus 2 plus 5 plus 10 plus 17 plus 26. And we don't actually need too much to engage too many brain cells to see that this one will diverge because you keep adding larger numbers. The series are either convergent or divergent. Now, what are the power series? Power series are going to involve a variable x, so that's like a next level. Understanding, kind of trying to put this in a context of comparing it to the basics of mathematics that you studied before you've seen this stuff. Studying the sequence is almost the same as studying just numbers, understanding what the regular rational numbers or irrational or something is. And then series would be basic operations on those numbers where you just add them and subtract them, and you ask whether they add to infinity or not. And then you upgrade those concepts of computation in your basic math into ideas of functions by introducing the variable. And you have x plus 2 and x plus 7 and so on. So now we are introducing concept of that variable x in the power series into a series, creating it as a power series, and then you can have x to the n. So the same thing, like you're going to have either x plus 2 or x squared plus 2 or x cubed plus 2. Over here you are going to have x to the n, which is a series of x to the n, and then you might have some other stuff around which would create the power series. So once you go a step further, you create a power series. Usually we say Cn x minus a to the nth exponent go from 0 to infinity, and that's the good old power series. Now, you have to understand that this power series is an infinite polynomial. Now, depending on how much you remember from your Calc 2 class, right, these power series, right, call them Taylor series in some cases. They're not all Taylor series, some of them. These power series are actually polynomials. So what this is equal to is when you have n equals to 0, you just have C0. And then you have C1 times x minus a plus C2 x minus a squared plus C3 x minus a cubed plus, and that's going to go forever like that. Now, if you carefully observe this, you see that it is a polynomial, right? If you just keep C0, that's a horizontal line. If you have C0 and C1 terms, that's a linear. C0, C1, C2, it's a quadratic. So all of that stuff. So this is technically a series, infinite series of polynomials. Now, power series are extremely important to us because we are able to, using the Taylor polynomial, right, Taylor expansion, we are able to take any function, well, not really any, but good amount of them, and write it as a power series. And when we do that, we are able to integrate and differentiate and perform operations easier than when we had the original functions. So to give also example of that, one of my favorite examples when I teach Calc 2 is to make a big point. Why is the derivative of sine cosine, right? And yeah, there is that proof in Calc 1 that is, you know, f of x plus h minus f of x over h, and it takes time to do that limit, and you have to know some identities and some limits and so on. But that proof is really long and painful. If you know how to obtain the power series for sine, it will be in this form where you are getting a polynomial. And then you differentiate that one, you will get a different polynomial back, and when you transform that polynomial, it will be a cosine. So it is really interesting to see, you know, how it works that way. So here we go. The sine x is defined, well, not defined, is equal to, that's a theorem. So n equals to 0 to infinity. We have negative 1 x to the 2n minus 1, sorry, 2n plus 1, divided by 2n plus 1 factorial. So this is a power series representation, negative 1 to the n. There we go, it's the oscillator. So this is power series representation for sine. Now, when you have this power series representation for sine, we can actually write this out as a polynomial by simply substituting n equals 0, n equals 1, n equals 2. And we're going to do that because we need it. So this is equal to, and now in expansion, when n is equal to 0, negative 1 dies. We get x to the first power divided by 1 factorial, which is just 1. So x divided by 1 is just x. So the first term is just x. Now, second term, n is equal to 1. Negative survives this time around. And then when you do all the calculations with n equals 1, you have to get x cubed over 3 factorial. Then the next term, your n is going to be 2. Negative 1 squared is positive 1, so negative sign dies. And then we get, when you carefully calculate everything, this. The next term will be that. The next one will be this, minus, and it will flip-flop like this forever. Now, the question is, how accurate is this? And the answer is it's pretty damn accurate. Because just with a few terms. You've heard in physics when you did your simple harmonic motions, I did those air quotes, you have that nonlinear term. We've seen that nonlinear term when we did our oscillations and our derivations in our class, right, in the previous chapter. Put that on a test, right? So we've seen that nonlinear sine theta in there, and we didn't like it because it makes solving that equation very hard. But what we do instead is we can replace that sine theta with just theta, like sine x, replace it with x. But we say for small theta. And the reason is that we see that our original function sine x, right, our original function sine x is has x as the first term. So in some sense, that first term carries the most, again, air quotes, the most of the function is there. Oh, come on. There. So if I am to just quickly graph this two, we know that the sine function, oops, come on. Sine function does something like this. And the y equal x function is the 45 degrees. Now, we see that there is a good amount of agreement between the y values of sine x and x in this area here. Now, we know that this one over here is pi over 2. So for small angles up to, I don't know, 15, 20 degrees, they are in a pretty good agreement with each other, and we can replace that with this. Now, what happens if you use the first two terms, right? You use x and then x cubed term. Well, if you just use that one, you are getting a cubic function, and you know how cubic function wraps. So your sine would look like this again. Right, so we have a sine function there. And the cubic function now would look like this. Oops. There is much more agreement between the polynomial piece and the sine function. And then if you toss in a fifth order, that would bend this up and would bend this down, right? And it would keep agreeing with the function better and better and better. So these power series are only equal to a function when you use all infinity of terms. Well, we're not elves. We can't sit there and, right, calculate that forever. So we say, what's good enough? How many terms do I actually need? And it turns out that you usually need like 3, 4 terms and you're good to go, right? Because that already brings you to the 4th or the 5th decimal precision. We don't get to build things that have that much precision in it. So, you know, I mean, you build a car, the tolerance is what? 0.001 or something like that, which is good for even first 2 terms. So we see now that we can replace sine x function with the infinite polynomial. And we call that Taylor polynomials, Taylor approximation, right? So I can write that this way. And now my question was, what is the derivative of sine x? Well, I can take the derivative of this, right? And I take the derivative of this, that has to be the same as the derivative of sine x, because I put the equal sign in between. I have infinitely many terms there. So now, the derivative of sine x hey, you just worked. Come on, pen. It works only when I don't need it. So the derivative of sine x, I have one red. Would be the derivative of this polynomial. And we know how to take this derivative. The derivative of x is 1. Come on. So take these derivatives. One minus 3x squared over 3 factorial plus 5x to the 4 over 5 factorial minus 7x to the 6 over 7 factorial plus 9x to the 8 over 9 factorial minus, and that's going to go forever. Now what happens with this is, well, actually first we cancel. Oh my God, this is... There we go. That's still not working properly. So 1 minus 3 factorial is 3 times 2 times 1, so 3 is cancelled. So I get x squared over 2 factorial plus 5 and 5 will cancel, x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial because 9 is cancelled, and that's going to go like this. So now, when you compress this, if you pay attention to the pattern, you will see that you again have the alternating piece. So I have negative 1 to the, if I start n at 0, that should be to the n, right? Because the first term has to be positive. And then I have x to the 2n, because all exponents are even, divided by the even factorial. Even numbers are 2n. So that is cosine x. Now, a lot of mathematics kind of fits quickly together if you observe this, because first of all, through this power series here, we show that the derivative of sine is cosine, because we followed all of the things. We also shown that expansion for sine are all odd exponents, leading it to be an odd function. And all of the cosine are even, leading it to be even. Now, you were told in pre-calculus course, trig course, when you took it, that you need to memorize that sine is odd function and has that property and a cosine without any further explanations, right? That was just stated, and you memorize it and you keep living your life. But when you do this one calculation here, you see how the power, the even powers for cosine, the odd powers for sine, and yeah, sure, there are those symmetries and things that we could use to explain things, but over here is clear. I mean, we see immediately what's going on. So these power series are insanely useful because they can turn a nonlinear function as you can see, sines and cosines, but also e to the x and everything else, into polynomials. Polynomials are easy to integrate, polynomials are easy to differentiate and to do operations with them. They're nasty to find roots, right? But we generally don't look for roots, we are looking for equations in this case. Now, what else is very important? Do you have to memorize all of the power series? The answer to that question, and for this course, is no. However, you know, down the line, you might be using them so much, depending on where you transfer and how you transfer and which major you transfer into. You might be using these on a literally daily basis, in which case you will memorize them just because you use them so much. You know, you use 3 plus 7 is, and you will say 10 because you use that a lot for the last 20 years. So the power series that you want to have on your radar at all time, because they show up all the time, are obviously e to the x sine and cosine, and then hyperbolic sine and cosine, and then some of the other very basic ones. Well, tangent is not listed, but should be that. So ln of x plus 1 and 1 over x minus 1, sorry, 1 minus x, are also on that list. So the textbook lists these, but then again, you might want to, you know, study these on your own to kind of figure out what's going on. So we have power series, n starts at 0, goes to infinity, and x to the n divided by n factorial. I hate when the pen starts bleeding like this. Does this yours? Does this? It's really annoying. And I have to make sure that I'm lifting it. And what do I have? 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and it's going to go like that. You pick up the pattern, right? Technically, the stuff that's missing here is over 1 factorial and 0 factorial. 0 factorial is also 1. So 0 factorial is 1 and 1 factorial is 1. Cool. So that's e to the x. Now we have a sine and cosine, which you have above. Look up. Then we have a sine hyperbolic x. Now, sine hyperbolic x is going to have the same thing as the sine x, except there will be no alternating term, negative 1 to the n. So we are talking about summation, n starts at 0, goes to infinity. We have x to the 2n plus 1 divided by 2n plus 1 factorial. We are just tossing out the negative 1 part. And for the cosine hyperbolic, we do the same. So the only thing that it's going to be missing there is the negative 1 alternating piece. The rest remains the same. All right, so those are the basic ones. Now, how does this look like? We have the same expansions, except no negative signs, obviously. So for sine, it's going to be x plus x cubed over 3 factorial plus x to the 5 over 5 factorial plus x to the 7 over 7 factorial. It's going to go forever. And for the cosine is 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, x to the 6th over 6 factorial, going on forever. Ln of 1 plus x, and if you just need ln of x, you just do the substitution and plug stuff in. I'll show that very soon. Summation of negative 1 to the n plus 1 times x to the n over n. So from 0 to infinity. No, that one starts at 1. You can't have 0 in it's divided by n. And that's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So in this case, you don't have the factorials. Plus goes forever that way. And then, just for the sake of what is the power series for 1 plus x squared? No coefficient, right? If you take a look at your exponential, right, you have this divided. So you do have 1 plus x squared plus x cubed, but they're divided by n factorial. Now, if you are just to say, okay, I have a power series, there's just 1 plus x squared plus x cubed. Now, where does that come from? Oh, I wrote it too far. Right, well, so that's clearly a series of what? Just x to the n, right? Starting from 0 to infinity. Now that one turns out to be 1 over 1 minus x. So that function, when expanded. So these are the power series. And I know they look nasty and crazy, but you spend some time with them and then it makes sense. Now the question is, and I mentioned this before, what do we do with the function composition for power series? Can we combine power series, get a new power series from old by combining them in some sense? And the answer to all those questions is yes, obviously, because it's math and it's awesome. So say that you have to expand e to the x squared. Why? Because you were supposed to integrate that monstrosity and you know nothing works, right? You know nothing works because it's not a use sub problem, you can't do by part, you can't do any of the stuff you learned in Calc 2, but you still need to integrate 1 over x squared. You actually don't need to integrate e to the x squared as much as you need to integrate e to the negative x squared, which is the bell-shaped curve. So if you want to have any of those proofs and things done for statistics that it's calculus-based, like the one they have in NGIT, you would have to know how to integrate that monstrosity. Now, what's the better way of integrating than just turning it into a power series? But there is an issue. You know power series for e to the x. Why? Because I wrote it, and from now on it's understood. You know it, right? So you are very familiar, right, with the e to the x expansion. But the question is, what's e to the x squared? Well, that's when you yank out every single x and you put x squared instead of it. Function composition. It works. So this is going to be the regular e to the x with x squared plugged for hx. So that's going to be what? 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial, and then go on forever. So as you can see, what is the first thing that you conclude about this function? Just by looking at it. You are looking at its expansion. What can you conclude? Well, it is divergent, but actually no. Yeah, it actually is. But what else? Look at it. What kind of function is this? It's even. And as soon as it's even, it's symmetric on the y-axis. All of these things immediately work together. So you have exponential growth, and then you have it squared, right? So When x is equal to 0, you only survive with the first term, so y-intercept is 1. It's going to go like that. Now grow fast. Go. So we are able to understand our functions much better, their properties much better, by turning them into power series and then analyzing the power series. So there we go. We have that piece. Now we are going to continue exploring this, and this is now going to be new stuff. You learned in Calc 2, in section 9.4, how to integrate and differentiate with power series. But you didn't actually differentiate power series, you differentiated the expanded part of it, right? What we want to do now is we want to actually differentiate the power series. So is there a way for me to differentiate power series in that compressed form while it's under the sum to get the solution without exploding it and then differentiating and then condensing it back? Right? It will be a significant time save if I can do that. So my good old sin x friend, which is summation n goes to 0 to infinity of -1 to the n and then x to the 2n plus 1 divided by 2n plus 1. Can I differentiate this? And the answer is, hell yes. I'm differentiating in respect to x, and this term has no x to it, this term has no x to it, so that's a coefficient, that's a constant, right? Now let me actually do that on stream. So when I'm differentiating in terms of x, this and this both do not have any x's in them, which means those just get copied. Also, I have the x to be a polynomial-like term, right? It's x to some kind of power. Now we know how to differentiate that. You drop the power, subtract 1. So we are technically not doing a lot of new stuff. So if I want to find now the derivative of sin x as taking the derivative of the summation of all of this, first, I understand that we have the, when I see the power series here, first we understand that I have a summation. If I am differentiating if I'm differentiating in respect to x, I know that I can differentiate term-wise. Yeah, there are infinitely many terms to differentiate here. Cool, right? But I also know that derivative of a sum is the sum of derivatives. So I can interchange this and have it like this now. So I am differentiating only this expression inside, and further this -1 to the n over 2n plus 1, that's constant, so that as well can go in front of the derivative. And all I'm differentiating now is this x to the 2n plus 1. Now that's a joke, right? Because differentiating that is just going to give me a basic polynomial. So I still have my summation. The integral n goes from 0 to negative 1 to the n, 2n plus 1. And now what do I get? I get 2n plus 1 times x to the 2n. All right, but and there is one issue that I still have to address, because we have to switch this to n equals 1 when we do the derivative. Now I'll need to explain that, and I'll explain that through integration. But let me just cancel these guys first, right? And when I cancel those guys, right, you see that I get this. And then there is a stuff missing here, right? Because I need this, in order for this to be cosine, I need it to be divided by 2n factorial. Oh, holy nightmare. I forgot my factorials along the way. I forgot my factorials. There we go. Let me redo this part here so it's easier to understand. So this is going to be 2n plus 1 times 2n factorial when I peel off the first one. There we go. And now when we 2n plus 1, okay, and then x to the 2n, because we took away 1 after differentiation, then these guys die, and you have. Now I'm going to immediately switch this to 1 because the counter shifts. And I will explain that in a second. Now, why would the counter shift when we take the derivative? Actually, I already taken the derivative here, so this one is 1 as well. I have to account for plus c. You know when you integrate and there's a plus c part? So if I'm to go back, I need that plus c. So that's the extra term. I shouldn't be saying this in context of counting numbers, that, you know, if you start counting from 0 and you go to infinity, and you start counting from 1 and you go to the 0, then this one has one more term. That's mathematical sacrilege. But because the set's uncountable, they go to infinity both, right? But the thing is that there is an extra constant term. When I plug in c equals to 0 over here, it kills the x part, and that's that first term called x, right? For cosine, you have 1 there. If you integrate that 1, what do you get? You get x back, right? But then there's also that plus c situation. So counter shifts by 1, and every time when you take the derivative, the counter will shift by 1. So you have your first stage of a power series. You differentiated once, n goes to 1. You differentiated one more time, it goes to 2, and 3, and so on. And those of you who sat in my Calc 2 class, what did I say? I said eventually in differential equations you will have to learn how to shift counters so you can solve differential equations. Well, welcome to that sometimes. It's now. In order for you to solve differential equation, you will have y, you will have y prime, you will have y double prime, and when you plug these things in, one is the function, one is the derivative. Counter starts at 0, counter starts at 1, counter starts at 2. You can't combine them because they all started at different counters. And you have to combine these functions together in order to get one power series for everything, which is the solution. So we also have to either learn or refresh. For some of you is learn, because you might not have done it in your Calc 2 class. And for those of you who took Calc 2 with me, definitely refresh, because I know I make a point about talking about it. So now, this is our this is how we do the derivatives. Now let's go and talk about counters and how the stuff works. So I'm going to just take a look before your heads explode at the basic power series definition. Say y is equal to just series of something simple, Cn x to the n. Can't have anything simpler than this. So this is literally your 1 plus, right? This is the basic one. So C0 plus C1x plus C2x squared plus C3x3 and so cubed and so on. I find its derivative, y prime. The counter shifts by 1, and I get n times Cn x to the n minus 1. I take one more derivative, because usually we solve second order, sometimes third order, but you'll see that you need a page per order. How about that? On solution. So now it's n equals to 2, and I will have n minus 1 Cn, which is what you copy, and then xn minus 2. So what I did is I took the derivative, and I took the derivative in respect to x, which is the reason why we copy Cn, right? That's in terms of n, not in terms of x. So that gets copied, and then we have this x. Now, what do we do next? Shift the counter. Because let's say add those. I just want to add them. All right. So I just want to go y plus y prime plus y double prime. All of this will eventually have constant coefficients in front, different functions in front, right? We'll have to massage all of that together. But right now, all I want to do is add these. Now, if you're looking at these, I can't add them because they don't have the same counter. If they had the same counter, I can just say, you don't say factor out summation. That's terrible. But because it's the operator, you don't factor out operators. You don't factor out multiplication or ln. That doesn't happen, right? But in order to put everything under the same summation symbol, they actually have to match the counter. And clearly counter is 0, 1, and 2. So let's learn how to shift the counter. Now that's going to be done in red because it's extremely important for this section. Shifting the counter. So I'm starting with my y prime is equal to summation n goes from 1 to infinity of n Cn x to the n minus 1. And I want to get, see, word get is much faster to write than achieve. Counter to start with 0. So that's my goal. Now, how do I achieve that? Well, I'm going to use a substitution here. First of all, clearly I get that when I subtract 1 on both sides. That should be common sense. So what I'm getting now is summation n minus 1 is equal to 0. Cool. So I have my counter now be equal to 0. But it's n minus 1 here, right? So this is where your substitution k is equal to n minus 1 kicks in, because I'm replacing this mess of n minus 1 with a single variable k. That's a new counter, right? But then the rest of the problem is in terms of n. So now they all have to change into k's, because you don't get to pick and choose which ones you change and which ones you leave. So now the whole thing becomes k goes from 0 to infinity. Please don't change infinity when you add 1 to it. Or subtract 1 to it. It stays there. Now observe that if k is n minus 1, then n is k plus 1, right? So we have k plus 1, c to the k plus 1, and x to the k. Ah, that's nice. That's really nice. And now, a move that as a student frustrated me so much. I literally lost nights of sleep over it. Or even when I fell asleep, I just wake up in like tears and all sweaty and angry. Let's just say, and I'll just write it as n. It's okay. Whew, I was furious about this. Because the first equation and the last equation have nothing to do with each other. I'm using the same n. There's equal sign in between them. What the hell? Well, in the great scheme of things, you have this Cn, which plays the role of this great equalator between these two worlds. So yeah, you're allowed to do this, actually. I understand now, but as a student, whew, I was furious. So what you see here is the entire procedure. You will subtract whatever amount you want to get rid of on both sides. You will arrive to this equation when it's equal to 0. You will get rid of whatever the hell you have here with the new substitution, transform everything, and then just break back the end. Now, in your notes, you have that second derivative. Transform that one back to 0 as a practice right now. Pleasant. So you have your second derivative, right? I'll write it here. The y double prime, which I just gave you, was summation n goes from 2 to infinity of, I believe it was n minus 1 times n times cn times x to the n minus 2. Right? That was the derivative. Go ahead. Transform that one so n is 0 on a counter. You have the steps. I'm not going to move it from the. I'm not going to move the steps from the screen. You have 18 seconds. Oh, I have a message. 19. that was way too much time. So let's shift the second one. So y double prime was n2 to infinity. And what do I have? I have something here. N minus 1 times n times Cn times x to the n minus 2. Come on, 2. There we go. So the same as previous, I will subtract 2 on both sides because I need to get it to equal to 0. That's summation n minus 2 equals to 0 to infinity. N minus 1, n, Cn, and then x to the n minus 2. Now n minus 2, I'm going to say that's k. So sub k equals n minus 2, from where n is k plus 2. So once I use that substitution, I will get k starts at 0, goes to infinity. Now n is k plus 2, so this is going to be k plus 1. And then n is k plus 2. And then c of k plus 2, and I don't have enough room for x to the k. So I found out that the second derivative, when I sub back n is 0, n plus 1, n plus 2, Cn plus 2, x to the n. And now I can add them. Now I can add all of these. So y plus y prime plus y double prime is summation n goes from 0 to infinity of Cn x to the n plus summation n goes to 0 to infinity of, what was that, n plus 1 c to the Cn plus 1 plus x to the n plus summation n goes to 0 to infinity of n plus 1, n plus 2, Cn plus 2, x to the n. Now if you carefully observe, all of the counters start at 0. So I can use one sum to pull all of these together under one sum, because all of the counters match. And observe that each one of them has exactly x to the n power, right? And because it has x to the n power, I can factor that out, leaving something that it's called recursion equation, which will be the center focus of our solution to differential equations. So what do I have here? I have Cn plus n plus 1 Cn plus 1 plus n plus 1 n plus 2. Oops, this is supposed to be a 2 over here. Cn plus 2, everything times x to the n. You cannot obviously take x to the n in front of the sum, because sum operates on n's, and that's exponent on x. So none of this goes out of the sum. It's all within. So as I said, this part here, obtaining this, is what you will need as we go into the next section to actually solve differential equations using these methods. So we understand power series, hopefully. We know that the power series are these polynomials that we get right from functions. And then we understand that they can be written out in terms of the exponents, right? X to the first and x to the second and so on. And then we understand that we can differentiate them either term-wise, if you look at the exploded form, or you can differentiate the entire power series, making sure your counter is shifted by 1 every time you take the derivative. Once you have that situation, you will actually have to shift that counter back. into n equals 0, so you can combine all of these things into one equation. And that takes care of this question. Let me just see if there is anything else in this introductory section. Multiplying, adding, dividing power series, that's all there. Shift of summations, that's explained on pages 200 and 201, which is what I just did. Radius of convergence of power series, if you remember that from your Calc 2 class, was done by using the ratio test. Very good. You use the ratio test. You divide AK by AK plus 1, and then you set that whatever you get there, you set that less than 1, and then you are looking for because you're looking for convergence, that will give you the domain. So that doesn't change from Calc 1. We are not going to actually use that. That's more of a theoretical part for this. Again, the functions that are already used for you as engineers, because we don't have math majors in the room, in terms of engineering, all of these things are already defined and checked, and in terms of theory by mathematicians. So it goes math and then physics and then engineering, right? So it's been filtered through the system, enough for you as engineer to use it. So we are not going to have problems to find radius of convergence and so on. Those of you interested, you guys can definitely take a look at the Calc 2 procedures and talk to me, obviously. I can show, but it's a ratio test, as Dian said, and we just grind through that calculation if need be. So I will show this one more part, which, I already kind of did that because I combined all of the power series under one, right? You can do that only when the counter matches, so that's something that it's important to know. One thing that I don't have here is multiplication and division of power series. Now, how much do you have here? And the answer is you have infinitely many things to divide or multiply. Technically, we would look into first, as I said, 3 terms or so, and you will multiply those out. So if you have, which was the problem from your calculus 2, where you had to do, if you remember, I called those of you who took Calc 2 with me, I called it an evil problem, the integral of e to the x times sine x. So integral of e to the x sine x dx, and we had to do 2 integration by parts to solve this problem, and then that trick to move the integral to the other side and divide both sides by 2. So it took a page, right, to solve that problem. And you might or might not remember this problem. And then I showed you a 3-step solution for complex variables, using complex variables, which those of you joining me next week for those extra complex variable lectures, you will see that on day 3 done again, except in that lecture I'm actually going to convert back from complex into the original sine cosine answer. But can power series make a joke out of this? And the answer is yes, because I can say that this is approximately equal to, right? Just see, this is a little bit flimsy. So this is approximately equal to the integral of, so e to the x, and I'm just keeping first 3 terms, because I did put approximation, not equal sign, so I'm not keeping infinity of the terms. So e to the x expansion, we know it's 1 plus x squared over 2 factorial, which is just 2, times, and sine x expansion, we know it's x minus x cubed over 6 plus x to the 5 over 5 factorial is 120. dx. What do you see here? You see two trinomials, which when you multiply through, you will get 9 terms, yes, but they're all polynomial terms. And it's a joke to integrate that. So you will get some stuff that will actually not be exactly what the answer to e to the x sine x dx is, but this is good for approximations. So if you have to, let's say, compute this integral from, let's say, 0 to 1, you will do the expansion of these functions either around 0 or around 1 or around half, depends on what, if you like pain. And you can do the expansion around that. I mean, you have to be very careful, guys, in mathematics if you're expanding things using power series to expand around the relevant point. If you have to compute the integral for energy or whatever, and it's 12 to 100, and you expand around 0, obviously your answer is going to be terrible, right? So as you are expanding functions, you better expand them around points where that function is relevant to you, not wherever is convenient. So I understand that the most convenient situation is to expand around 0 if it's possible, if there is no vertical asymptote. But again, if you are doing a computational problem and you have to find the integral 6 to 7 and you expand to 0, your answer will be garbage. It has to be, right? Because it's just far away. If you have integral 6 to 7, your expansion has to be around 6. 6.5, I don't care. But it has to be in that range. The expansion point has to be in that range. It also depends on how well the functions are behaved and so on. There's a lot more mathematics coming out down the line if you're interested. So you'll figure those things. And I'm just going to say over here now, no. First, multiply, then integrate. And the key is that this is approximation. So you can, in fact, multiply power series. Now, I truncated, that's the word for when you throw away, a whole bunch of infinite amount of terms, actually, and you keep just few. So I truncated these two series by throwing a lot of these terms out and keeping only first 3 for each one. I could have left all of the terms in there, except I would never be done multiplying, right? Because they both have infinitely many terms. That should go without a say, right? Division of these, again, equally annoying. You divide one by another and you just keep doing it. They did it in a book, and there's no way in hell I'm going to actually, sit there for like 3 hours and work it out. You can find that on page 198, and you can see it's the entire page. It's one long division of polynomials. Again, power series right in this form are polynomials. So if you know division of polynomials, you should be able to grind through this stuff and understand it if you're interested in how to divide power series. So power series can be added, they can be subtracted, they can be multiplied, they can be divided. They can be, raised to a power. Taking a square root of that is no, obviously, because you don't get to take a square root of, x plus 3. Even square root of x squared plus 16, also you don't get to take a square root of that because of the plus, right? So there's nothing you can do. So this is what we have for our rules: addition, subtraction, and obviously if this was y plus y prime plus minus y double prime, then you would have a minus in front of the last series, and then there will be a minus in that. So that minus would just propagate down and you guys will have a minus there. So this is all we have. There's a little theorem, should I say, that two series are identical if their counters start at the same place and they have x to the n, or so these two would be identical if Cn is the same as n plus 1, Cn plus 1. They would be identical because x to the n, and 0 and 0. Right? So There is this theorem. It's worth mentioning. So two series. Let me put it this way. If. There we go. If summation n starts, let's say, at 0 to infinity of a n x to the n is the same as this one, then a n equals b n. So this is just how to, equality of these things. And now we're going to take a few minutes to reset the brain. And then after that, 3.2 solutions near ordinary points. So we are going to solve some of these differential equations now using this method. So let's take a few, and then we'll come back even stronger and more determined to do these things.